All right, let's get into it. Ever stop and wonder how your computer is, well, doing everything at once? Today, we're going to pull back the curtain on that magic. We're talking about the core ideas, processes, and threads that make all of our modern multitasking possible.
Yeah, just think about it for a second. Right now, you've probably got your web browser open, maybe some music playing, your antivirus is almost definitely doing its thing in the background. So how? How is one single computer doing all of that seemingly at the exact same time without just completely seizing up?
The secret, the real magic here, is all thanks to the operating system. It's the master controller of your whole machine, the real unsung hero making it all work. And hey, by the way, if you're a bit fuzzy on what an OS really is, you should definitely check out our OS playlist first. It'll give you all the fundamentals you need before we dive deeper here.
Okay, so here's the game plan. We'll start with the illusion of multitasking itself. Then we'll get to know the stars of the show, processes and threads. And we'll wrap up by looking at how the OS acts as the CPU's own personal traffic controller to manage all this chaos.
All right, first up, the illusion of multitasking. Let's break down how just one CPU can create this incredible appearance of doing a million things at once.
So here's the big secret. Your computer isn't actually running your browser, your music, and that antivirus scan all at the exact same nanosecond. Nope. What's really happening is the CPU is switching between these tasks insanely fast. We're talking milliseconds. It's so quick that to us, as humans, it just feels like everything is running at the same time. That's pseudo-parallelism.
So how does the OS actually pull this off? How does it organize all these running programs? Well, that brings us to our next big idea, processes. This is the OS's fundamental unit for managing any running application.
So what is a process? Well, the easiest way to think about it is as a program in action. The moment you double-click that app icon, the OS doesn't just run the code. It builds this special container around it. And that container, that's the process. It holds everything that program needs to do its job. All the code, the memory it's using, any files it's got open, the whole shebang.
And a process isn't just static. It's constantly changing its state. It can be in the ready state. Basically, it's in line, waiting for its turn on the CPU. Then boom, it gets its chance and moves to running, where it's actually being executed. But if it needs to wait for something, say for you to type something or for a file to download, it goes into a blocked state. And that's super important, because that frees up the CPU to go work on something else.
Now, you might be wondering, how on earth does the OS keep track of all this? With hundreds of processes, it sounds chaotic. Well, it has a little cheat sheet for every single one called a process control block, or PCB. Seriously, just think of it like an ID card for the process. It's got everything, its ID, its current state, and maybe the most important piece of all, the program counter. That little guy tells the OS exactly which line of code to run next. It's the key to how you can pause a process and then pick it up right where it left off.
Okay, so processes are great, but they have one big drawback. They're kind of heavy. Creating a whole new process with its own private memory and all those resources, that takes time and energy. So what happens when a single app needs to do multiple things at once? Like, think about your word processor. It's checking your spelling in the background while you're still typing. If it had to create a whole separate heavyweight process just for the spell checker, man, your computer would grind to a halt. It's just way too slow.
And that's where our next hero comes in, the thread. You can think of a thread as a lightweight process. It's a much smaller, much faster unit of work that can run inside a process that already exists.
The absolute key difference here is all about overhead. Processes, as you see, each get their own separate, walled-off memory space. That's awesome for keeping things secure, but it makes them slow to create. Threads, though, they all live inside one process, so they share the same memory. And because of that, creating them and switching between them is lightning fast. It's way, way more efficient. There's a really fantastic analogy for this that just makes it all click. Think of it like this. A process is like a house, and a thread is like a person living inside that house.
And this just explains it perfectly, doesn't it? The house, the process is just the container. It has all the resources, right? The kitchen, the bathroom, the electricity. That's like the memory and the files. But the house itself doesn't do anything. It's the people living inside, the threads, who are actually doing the work. They're the ones cooking, cleaning, and moving around, all sharing those same resources.
Okay, so let's zoom out. We've got all these processes and inside them potentially hundreds of threads. And they are all fighting for time on a very, very limited resource, the CPU cores.
You've basically got a massive traffic jam on your hands. So, how does the OS play traffic cop? Who gets to go, when do they go, and for how long?
Well, that brings us to a super important part of the operating system called the scheduler. And yeah, it's the CPU's traffic controller. Its one and only job is to look at all the tasks that are ready to go and use some kind of smarts, an algorithm, to decide which one gets to use the CPU next. To really see this in action, let's walk through a simple example. Imagine we have 5 jobs, let's call them A, B, C, D, and E, that all show up at once. And as you can see, they each need a different amount of time on the CPU to finish up.
All right, strategy number 1. First come, first served. This is the simplest approach you can imagine. It does exactly what the name implies. You just handle the tasks in the exact order they arrived. No funny business.
So if we follow this timeline, process A, our big 10-minute job, goes first. But look what happens to poor little process C. It only needs 2 minutes of work, but it's stuck waiting around for a full 16 minutes before it can even start. This is a classic problem in scheduling. It's called the convoy effect, where a bunch of short, quick tasks get stuck behind one long, slow one.
If you do the math, the average time it takes for a job to finish, what we call the turnaround time, ends up being 19.2 minutes. I mean, it gets the job done, but you gotta ask yourself, can we do better?
Okay, let's switch it up. Strategy 2 is a bit smarter. Shortest job first. Here, the scheduler's clever. It looks at all the jobs waiting and says, hey, which one is the quickest? Let's get that one out of the way first.
And just wow, look at the difference. Process C, that little 2-minute job, runs immediately and it's done. Then D is done. Then B is done. You get all the quick wins out of the way fast. Yeah, the big 10-minute job A still has to run, but we save it for last, after it's not holding anyone else up.
So what's the result? The average turnaround time plummets to just 14 minutes. That is a huge improvement. And it's a perfect example of how picking a smarter scheduling algorithm can make a massive difference in how responsive your entire system feels. So let's wrap this all up. A process? That's the house. It's the container with all the resources. A thread? That's the person living in the house, actually doing the work. And the scheduler? That's the traffic cop for the whole neighborhood, deciding which person from which house gets to use the main road, the CPU, next.
And that leaves us with a bigger question to chew on. As we start moving from CPUs with, 4 or 8 cores to chips with dozens or even hundreds of cores, what becomes more important for a scheduler? Is it making sure every single task gets a fair shake? Or is it about maximizing the raw total amount of work getting done, even if some tasks have to wait a little longer? That's a huge trade-off, and it's one of the big challenges that OS designers are grappling with right now. Thanks for joining me.